Next theorem on properties of subgroups of under homomorphism. Proof. What are given things? Phi from G to G bar is a homomorphism. Then H is subgroup of G. Therefore, what is phi of H? So phi of H is collection of all images of the elements H under phi. And what is, and if K bar is subgroup of G bar, then phi inverse of K bar equal to what is collection of pre-images in domain such that phi of K belongs to G bar. These are the some basic sets related with this homework. First thing, phi of H is a subgroup of G bar. First, claim phi of H is a subgroup of G bar. I have to prove this. As H is a subgroup, so identity belongs to each H, and we know that identity maps to identity under homomorphism. Therefore, E dash equal to phi of G, phi of E. This belongs to phi of H. So identity belongs to phi of H. So this implies phi of H is not empty. Now we'll apply subgroup test. If A comma B belongs to subgroup H, then AB inverse belongs to H. We'll do that. So for H1 comma H2 belongs to H, we have phi of H1 comma phi of H2 belongs to phi of H. Therefore, as H is a subgroup of G, implies H1, H2 inverse belongs to H. So this implies phi of H1, H2 inverse belongs to phi of H. Images belong to it. Now we have, for proving the subgroup, we have to prove that phi of H1 into phi of H2 inverse belongs to phi of H. We have to prove this. So therefore, phi of H1 into phi of H2 inverse. So this is equal to phi of H1 into, you can write this as phi of H2 inverse. But phi is a homomorphism. So this implies phi of H1, H2 inverse, since phi is a homomorphism. So this belongs to phi of H. So first element into inverse of second belongs to phi of H. This proves phi of H is subgroup of phi of G. There is the first part. And second part is If H is cyclic, then phi of H is cyclic. Second, let H cyclic means it is generated by some elements. H is generated by A, be a cyclic group. Be a cyclic group. To claim phi of H is generated by phi of P. We will have to prove this. Means every element of phi of H is some power of phi of P. So as H equal to, or H is generated by A, so every element of H is some power of A, by the definition of cyclic group. Therefore, what is phi of H? We can write this as phi of A raised to N, where N belongs to Z. But this is same as phi of A raised to whole N, where N belongs to Z. So phi of H, every element is in the power of phi of A. We can write it as generated by phi of A. Therefore, phi of H is cyclic. Third is, if H is abelian, then phi of H is abelian. Right? H is abelian. What is the claim? Phi of H is abelian. So for A comma B belongs to H, phi of A comma phi of B belongs to phi of H. Therefore, phi of A into phi of B equal to phi of A into B, since phi is homomorphism. Since phi is a homomorphism. But we can write this as phi of B into A. Since H is abelian, again we can write this as phi of B into phi of A, since phi is homomorphism. What we put here, so phi of A into phi of B is phi of B into phi of A. So this implies phi of H is abelian. This is third part. Now fourth one, what is fourth? H is normal, then phi of H is normal, right? Let H is normal subgroup of G. What this means? This implies for X belongs to G and H belongs to H, we have X inverse belongs to H. This is the definition of normal. This is the criteria. To claim phi of H is normal subgroup of phi of G. I have to prove this. So for that, we will consider let phi of H belongs to phi of H and phi of X belongs to phi of G. Therefore, phi of X into phi of H into phi of X whole inverse, we can write this as Phi of x into phi of h into phi of x inverse. So this is phi of x h x inverse since phi is homomorphism. So this belongs to phi of h because h is a normal subgroup, therefore x h x inverse belongs to h. So group element, subgroup element, and group element inverse belongs to subgroup. So this implies that subgroup is a normal subgroup. So phi of h is normal subgroup of phi of g. This is fourth one. What is fifth one? Fifth part is if order of given, let order of kernel of phi equal to n. This is the given thing. Claim. What is claim? Phi is an n to 1 mapping. N to 1 mapping of from G onto phi of G. This is the claim. What is n to 1 mapping? If this is domain, this is codomain, consider this as a function f. And f is 2 to 1 means any two elements map to a single element. Don't care about other things. Two elements map to 1. Other possibilities are also there. If these two elements map to this, and so such type of mapping is called n to 1. So n elements map to a single elements. So this is a n to 1 map. How to prove this? We know that what we know, if phi of g equal to g dash, then phi inverse of g dash, so phi inverse of g dash is g into kernel of phi. This is the left state of kernel. But for kernel, there are n. So for elements of kernel, we have n possibilities. So this implies exactly n elements, of G kernel phi. See here, for kernel of phi, there are n choices. So G kernel phi has n choices are mapped to phi of G, right? This implies phi is an n to 1 mapping, right? So this fifth one. What is sixth one? Let order of h equal to n. So claim, yes, order of phi of h divides order of h. This is the claim. Now, as phi from G to G bar is a homomorphism. So we will. So what is the case? This is the case. Suppose this is G. This is G bar, and this is the mapping phi. So we will restrict this mapping phi to h. So this is the mapping phi h from h to phi of h. So we will restrict this. So that is also homomorphism. Therefore, phi h from h to phi of h is a homomorphism, and let order of kernel of phi h equal to m. So by previous part, we know that this phi h is a m to 1 mapping. And such type of mappings, image of order set is order of domain divided by number of elements in kernel. Yes? So we can write this as order of h equal to the number of elements in domain are m. So m into order of phi of h. So this proves order of phi of h divides order of h. Okay. Now seventh one is, what is seventh one? Seventh one is given k bar is subgroup of G bar is subgroup of G bar. It is given. What is claim? We have already defined inverse. Claim is phi inverse of k bar is a subgroup of phi is a mapping from G to G bar. So phi inverse is a mapping from G bar to G. So phi inverse k bar is subgroup of G. We have to prove this. Okay. As again we know that under homomorphism, identity maps to identity. This belongs to k bar. So this implies E equal to phi inverse E dash belongs to phi inverse k bar. This implies phi inverse k bar is non-empty. I can write non-empty. Yes, first condition. Now let k1 comma k2 belongs to phi inverse k bar. Therefore, phi of k1 comma phi of k2 belongs to k bar. But k bar is a subgroup, as k bar is a subgroup of G bar. Therefore, phi of k1 into phi of k2 inverse belongs to k bar. This implies, but phi is a homomorphism. So otherwise, we get phi of k1 into phi of k2 inverse belongs to k bar. But phi is a homomorphism, so this becomes phi of k1 into k2 inverse belongs to k bar. That is k1, k2 inverse belongs to phi inverse of k bar. So k1, k2 belongs to phi inverse k bar implies k1, k2 inverse belongs to phi inverse k bar. Therefore, phi inverse k bar is a subgroup of G. Now eighth one. What is given in eighth part? Given K bar is normal subgroup of G bar. It is given. So claim phi inverse K bar is normal subgroup of G. You have to prove this. Okay. So for proving a normal subgroup, H is normal subgroup of G, we have to take one element H from H and one element from group and prove that X inverse belongs to H. Then H is a normal. So we have to take one element from phi inverse K bar, one element from G, and we have to follow. We have to proceed. Right? G belongs to G and X belongs to phi inverse K bar. We will prove what? G inverse belongs to phi inverse of K bar. Okay. Now, as X belongs to phi inverse of K bar, this implies phi of X belongs to K bar, right? And G belongs to G implies phi of G belongs to phi of G. As K bar is normal in G bar, therefore one element from G bar and one element from K bar, right? So that is phi of G into phi of X into phi of G whole inverse belongs to K bar. So this means you can write this as phi of G into phi of X into phi of G inverse. We already proved this when phi is homomorphism. But phi is a homomorphism, so we can write this as phi of G X G inverse belongs to K bar. Therefore, G X G inverse belongs to phi inverse of K bar. Hence, phi inverse of K bar is normal subgroup of phi of G. Oh, sorry, normal subgroup of phi inverse. It is normal subgroup of G. And 10th part is given phi from G to G bar is onto and kernel of phi is identity. That is, order of kernel of phi is 1. Therefore, we know that phi is a 1-to-1 mapping. If order of kernel is m, that is m, right? Now phi is 1 onto, phi is 1, 1, and phi is a homomorphism. That is, phi is operation preserving. Therefore, phi is an isomorphism. That was our target. So this completes this theorem.